video, we will be discussing some strategies that are useful in retrosynthesis. So there are 5 possible strategies here. The first one is consider different possibilities. Number 2, we try a number of disconnections and FGIs. And number 3, we try to keep the number of steps down and stick to known and reliable reactions. So in this third strategy, it is very important to keep the number of steps down. For example, if you are in the manufacturing sector, keeping the number of steps down, meaning decreasing the number of steps, which means will increase the efficiency of the synthesis and also will reduce some costs. Yeah. Okay. Strategy number 4. So in real life, a synthesis has to be economically viable, meaning that a synthesis has to be done in the cheapest way. I mean, the starting material must not be expensive, the step must be reduced, so the condition must be mild, so in order to ensure an efficiency in the synthesis and where it can reduce the cost. Yeah. Okay. Strategy number 5 is whenever it is possible, we should go for a convergent route rather than a linear one, as this will lead to a higher overall yield. Okay, let's take a look at how the difference between linear and convergent synthesis. Okay, if you look at the first example here, this refer to convergent synthesis. So in order to make A, B, C, D, F, so this A, B, C, D, F can be made from F, B, C, D plus E, F. Okay, so A, B, C, D can be made from A, B plus C, D, and this E, F can be made from E plus F. And then the AB can be made from A plus B, and CD can be made from C plus D. Okay, this is the convergent type of synthesis. Another type is the linear synthesis, where you have A, B, C, D, E plus F. So A, B, C, D, you need to form A, B, C, D, E, you need to form from the reaction of A, B, C, D plus E. And then this A, B, C, D is A, B, C plus D, and A, B, C is A, B plus C, and A, B is A plus B. Okay. Both of these assume 80% yields. Yeah. Okay, we now take a look at how it is different. Okay, let's see. If linear, okay, you have from A to AB, this is step 1. From AB to ABC, it is step 2. From ABC to ABCD, step 3, and go on until step 15, for example. Okay, if the first step is 80%, so assuming that all these steps are 80% yield, yeah? So if every step is 80% yield, at step number 15, the overall yield is only 3.5%, which is very, very low. You do not want to spend so much money or so much time on the starting material A to get to AP with only 3.5% yield. Okay, now let's take a look at what if we adopt convergent type of synthesis. So from A, we get AB, and so A, C, and E, so these reactions, they are all done simultaneously. So you form AB first, and then you form CD, you form EF. So assuming that all these steps give you 80% yield, and then in order to form ABCD, you react AB plus CD. So this is already 64% yield. and now you want to form ABCDEF, so you react ABCD with EF, so you get ABCDEF, and then at 51%, and then you get the last compound here is still around 32%, which is almost 10 times of the yield you obtain from a linear synthesis type of reaction. Yeah. Okay. And then apart from that, we also aim for greater simplification, or if we want to make something, we need to make it simple as possible. Okay, so how do we make it as simple as possible? First one, we make this connection towards the middle of the molecule. So when we disconnect in the towards the middle of the molecule, this is more to convergent way, not linear. If we focus on linear synthesis, we normally cut at the end of the molecule. But if we want it to be more convergent, we can make this connection in the middle of the molecule. And then the second strategy is we can disconnect at the branch points. Okay, and the third strategy is we use symmetry where possible. So towards the middle, almost similar to the point number 1. Okay, let's take a look at the example here. Okay, now we have this molecule. So we cut it towards the middle. So in this case, this part is the middle of the molecule. So when we cut it, we get this synton. We get this synton. And then another one here. Okay. So because it is minus, we can complement it with just hydrogen. And because this is plus, we can complement it. So it can become methyl vinyl ketone like this. So what happens is that when you have a ketone, you react it with base. Okay, base. And then you react with methyl vinyl ketone. So you will get a diketone compound. So if you can write the synthesis, it is using the concept of aldol reaction. Yeah. Okay. Now let's take a look at what happens if we cut it at the branch point. Okay, if you look at your compound here, it has quite a number of branch. So we cut it this way. We cut it at the branch point. So what we get is this part as the synton, and another part is this one. So this minus can be complemented by hydrogen here. Okay, and this synton is because it is plus, so it can become the alkyl halide like this. Yeah. Okay, so what happened? You have the ester. Okay, this ester, when you add base, so what happened? This alpha proton will be abstract. So you will get CH2 minus here. So it is a nucleophile. So what happened? This nucleophile will attack the most positive carbon, which is this one. And then the Br will leave to give you this target molecule. Okay, this is strategy at the branches. Now we take a look at the symmetry point. Okay, symmetry point, if you look at this compound, so you know that once you have double bond, you cannot cut the double bond yet. So what we need to do is we need to do FGI. FGI. In this case, we would like to convert the double bond into OH. That's why we do the FGI. Okay, the double bond is now turned into OH. Okay, once we get OH, if you see this OH and then this carbon and then another carbon here. So this means that this looks like an aldol compound. Okay, aldol compound is easy. We already know the chemistry of the aldol compound. So let's say we cut in the middle of the compound. So what we get is, this is plus, this is minus. So this is the synthon. And what is the equivalent here? You know that when you have a C plus next to OH, it will give you a ketone like this. And then this one, because it is minus, so you can just complement it with hydrogen, so you get another one. So the Se is like this, and this Se is also the same. Okay, so forward synthesis. So this is the forward synthesis or forward reaction. Forward reaction. So in the forward reaction, you introduce base. So base will abstract the proton from the alpha proton. So it is like this. CH, CH. So you have OET minus. So this will abstract the alpha proton. So this bond will move to here and you will get CH2 minus. So this CH2 minus will attack another ketone, which is attacking this double bond, C double bond O, and this bond will move here and you will get this compound. Okay, and after a while, this compound, when we remove H2O, or you can react it with H2SO4, which is this reaction is what we call as dehydration of alcohol. So you will get a double bond. So this is your TM, or the target molecule. Okay, sometimes it helps the retrosynthesis if you add a functional group to facilitate bond formation. So in this case, this is what we call as functional group addition. So if your compound does not have any good functional group, so you can add another functional group. So an example of this is where you can see in acetoacetic ester synthesis. Okay, so in acetoacetic ester synthesis, this is the target molecule. I mean, this is the product. So if you look at the product has so much alkane chain here. So what you can do is you can add functional group to it. So it is called FGA. So from these branches, you convert it into, this is the butyl, this is part the butyl, you add this functional group. So this is the functional group that you add, so that's why it is called FGA. And then once you have this functional group, you can do the disconnection and you disconnect this part. So you can synthesize this compound using ethyl acetoacetate as drawn here. Therefore, the forward synthesis or the forward reaction for that for that particular target molecule is where you have, this is the starting material just now, and then you react with base, so you will get CH2 minus, so this CH2 minus, and then you react with iodomethane, so you will get methyl group here. So this methyl group, and then this ester with methyl, and then you react with base and also butyl bromide, so you will get another butyl group here. So and then after that, this compound is now undergo some workup, and when you heat it in the presence of acids, so you will get the ester will be converted to carboxylic acid, and then after that you do some decarboxylation and you get the you get the product, yeah, the target molecule. Okay, that's all for strategy in retrosynthetic analysis. So I will see you again in the next video in how we can do retrosynthetic analysis on compound with latent polarity.